Okay, the third part of the equilibrium constant has to do with Kp. P simply stands for pressure, and so it's the equilibrium constant for a gaseous reaction in partial pressures. So it asks you to write the equilibrium constant expression, or Kp, for the following reaction. So instead of using brackets for the concentration, we're going to use P for pressure. So for example, the Kp for this equation is the partial pressure of NO2 squared divided by the partial pressure of N2O4. And so it's basically the same process. You write the product and then you put a power for whatever the coefficient is over the reactant to whatever power that may be. Here's another example here. This one's a little bit more complicated. So I have Kp is equal to the pressure of NO to the fourth, pressure of H2O to the sixth, over pressure of NH3, oops, I really got that subscripted, NH3 to the fourth, and pressure of O2 to the fifth. And that's all you have to do for these. It's just like writing the Kc expression. Now, we can convert between Kc and Kp using this equation. This is not given to you on the formula sheet because of the fact that it's a derivation of the ideal gas law from molarity. Okay? So because we're dealing with pressures, the R is the 0.0821. Temperature, of course, anytime we use R has to be in Kelvin. The delta N is change of the moles from the products minus the moles of reactants. And this is probably the hardest part of doing this equation, that and the fact that students don't want to use these parentheses. So if I look at this, okay, I have 4 plus 6 to equal 10, and I have 4 plus 5 to equal 9. So delta N is 10 minus 9, or 1. For this one, I have 1 mole of gas over here, and I have 1 plus 2 over here to be 3. So delta N is 1 minus 3 to be a minus 2. Okay, so that's basically what you do. The 4 came from the coefficient, the 6 came from the coefficient, the 4 came from the coefficient, and the 5 came from the coefficient. Okay, and you just sum those up. Now, I didn't point that out, but all of these are gases. If it's not a gas, it's not included in this count. Okay, it's only the moles of gas that are done. Okay, so here's a problem. It says that the Kc is equal to 0.025. So Kc is 0.0952 at a temperature of 227 degrees C. They want to know what is Kp for this equation. Okay, so the equation is that Kc is equal to Kp times the quantity of RT delta N. So delta N for this reaction is 1 plus 2 is 3, so 3 for the products, minus 1 for the reactants to equal 2. I'm going to need R, and R is 0.0821. It's a constant. And so I plug these in, okay. Oh, and the Celsius has to be in Kelvin, so this is at 273, and this is 500 K. Okay, so I plug this in. Kc is what I'm solving for. I have Kp, which is 0.0952, times the quantity of 0.0821 times 500 raised to the 2. So in doing this, I'm going to leave this first parentheses alone, 0.0952. I'm going to do the quantity inside of the parentheses, and I get 41.05 it's still squared. So 0.0952. If you wanted to go ahead and do this, you could, but I went and squared this, and I got 1685, and then multiply those two together, and I get 160. Again, the units, if I were to do the Kp expression for this, it would be atmospheres, well, I'm not actually doing it, but times atmospheres squared divided by atmospheres. So these atmospheres cancel, so my units are atmospheres squared. Okay. Last example for this section is this reaction. This is fluorine dissociates into its atoms upon heating. Okay. So I have a Kp that is 7.55 times 10 to the minus 2. I have a temperature of 842 degrees C, and they want to know what is Kc for this reaction. Okay, again, R is a constant, 0.0821. The equation is going to be Kc is equal to Kp times RT, and remember this is not given to you on the formula sheet, delta N. Delta N is 1 minus 1/2 to give me 1/2. Okay, so I have 7.55 times 10 to the minus 2. Kp is what I don't know, times quantity of 0.0821 times, oops, I forgot to add the 273 to get 1100 or 1115 K. Okay, and to the 1/2. So I'm not going to touch anything on the left. 7.55 times 10 to the minus 2 Kp. I'm going to do the inside the parentheses first, and I get 91.54 to the 1/2. Still going to leave this the same. 7.55 times 10 to the minus 2 is Kp. Now raising this to, and the easiest way to do this in your calculator, at least it is for me, is to put 91.54, the up arrow, 0.5 means the same thing. Okay. Then I get 9.568. So I'm going to divide both sides by this 9.568. So 7.55 times 10 to the minus 2 divided by 9.568 is equal to Kp. And I've been doing this, so sorry, wrong the whole time. Not only is the formula not given to you, I miswrote it. Sorry, Kp, Kc. I was doing it right, I just had the wrong subscripts there. So Kc ends up being 7.89 times 10 to the minus 3, or you could also write this as being 0.00789. Either way. Unit-wise, I have atmospheres on top. I have atmospheres to the 1/2 on the bottom. Okay, so I subtract these and I get atmospheres to the 1/2 as my units. And so that is the answer right there. And that is the end of this section, equilibrium constant, part 3.